Thank you very much, everybody, for coming on to another one of our Timescales of Mineral Systems group seminars. This month, we're very lucky to have Janne, who is going to be telling us a little bit about the PhD she finished over a year ago now.
1.5
years ago, about the rise of continents and atmospheric oxygen. Janne, please take it away.
Thank you. Yeah, as Milo said, I'm going to talk a little bit about my PhD work, which of course was undertaken in collaboration with many other researchers, and some of them are listed here as co-authors on my title slide. And temporally, my PhD was focused on the Archean Proterozoic transition, which I'm sure most of you know was a period in Earth history that was characterized by a number of fundamental changes. And I always like to start my talks on the Archean Proterozoic transition by showing these two images here. So on the left-hand side, we have an impression of how the early Earth may have looked like, with continents that were mostly submerged and an atmosphere that was mostly devoid of oxygen. And instead, Earth may have been covered by a thick hydrocarbon haze, leading to an orange sky color in the Archean. And then, in contrast, on the right-hand side, the modern Earth as we know it today, with large sub-area land masses and an atmosphere that's comprised by 20 to 21% oxygen. And many geoscientists have tried to answer this question of when and how did we go from this to this. So why should we care about continents and our atmosphere? Well, it has been argued that many of the habitable features of Earth are including our hydrosphere and our oxygen-rich atmosphere, and also our magnetic field that's shielding us from solar wind, are linked to the planet's interior. And that perhaps this coupling of the Earth's surface environment and the interior of the planet is an explanation of why other terrestrial planets like Venus and Mars, for example, that have a similar bulk composition, a similar size, and also similar distance to their host star, developed so drastically different to Earth, and today have surface environments that are hostile to life. So understanding of how processes governing the Earth's surface environment and the interior of the planet may be linked not only has implications for the history of our own planet, but also for the evolution of habitable planets in general. So, as mentioned, the focus of this talk is on the Archean Proterozoic transition, which per definition is at 2.5 GA. And as I already mentioned, this time period of Earth history was characterized by a number of secular changes, some of which may have had implications for the long-term habitability of Earth. So to understand what Earth may have looked like or what processes have been operating 2.5 billion years ago, we often rely on clues from the geochemical record, as this is often the only preserved evidence from this time span. So what I'm going to do is I'm going to talk you through a number of geochemical proxies that indicate changes around the Archean Proterozoic transition, and then what they may tell us. And I'm going to start with the zircon oxygen isotope record. The great thing to start with, so this curve that you see here is the moving average of the time-resolved global zircon oxygen isotope record, including both detrital and igneous zircon. And the great thing about zircon is that it provides a robust, if not the most robust, record of the oxygen isotope composition of felsic magmas. And in addition, we can tie these measured oxygen isotope compositions to an age through uranium-lead geochronology. So the gray bar here marks the compositional range of zircon that crystallized from mantle-derived melts, and delta 18O values above the mantle value, which indicates that they're isotopically heavier, are interpreted to be the result of supercrustal recycling or the assimilation of supercrustal material into magmas, as heavy delta 18O values arise from the interaction of rocks with surface water during continental weathering. And then in contrast, delta 18O values below the mantle value, those are less commonly observed, but they do exist. They are interpreted to reflect hydrothermal alteration. So the most prominent examples are from caldera environments. Yellowstone, for example, is very well known for producing low delta 18O magmas. So what does this tell us? You can see that throughout the Archean, the zircon-oxygen isotope composition is relatively constant. And then starting from the early Paleoproterozoic, we see an increase in average zircon delta 18O, indicating an increased importance of these high delta 18O supercrustal materials in these magmas, from which zircon then crystallizes. And in addition, we also see that starting from the early Paleoproterozoic, there is a greater scatter in delta 18O values, which you can see based on this 1 sigma envelope that I put around this curve. So interestingly, a similar trend has been observed in the shale oxygen isotope record. This curve there at the top of the figure shows the triple oxygen isotope evolution of shale expressed as cap delta 17O. And very similar to the zircon record, you can see that throughout the Archean, it's relatively consistent. And then between 2.4 and 2.3 GA, it's subject to a change, which, according to these authors, is best explained through a change in the oxygen isotope composition of surface waters that interacted with the continental crust to then form these sediments. And to achieve such a change in the oxygen isotope composition of surface waters, we require large subarea land masses because they allow for the strong fractionation of oxygen isotopes in meteoric waters. So this effect is evident from a correlation of delta 18O in meteoric waters with latitude, what you can see here in this figure at the bottom right, that shows oxygen isoscapes of mean annual precipitation. Strontium isotopes are another tracer for continental erosion and weathering, as the felsic continental crust is a major reservoir of radiogenic strontium isotopes. And the dashed line here is the seawater strontium evolution as inferred from the marine carbonate record. And this is actually something that was published relatively recently by Helen Shen last year. And I was super excited to see this come out because before she published this updated compilation of marine carbonates, the last compilation was from 2001, so about 20 years ago. And Helen's work added a lot of new data points to constrain this curve, especially for the Precambrian. So we're now able to constrain this increase in seawater strontium ratio, seawater 87, 86 strontium ratio to be precise, a lot better. And it occurred at some point between 2.5 and 2.35 GA. And this is commonly interpreted to reflect an increase in sedimentary runoff from the continents into the ocean. So the continents emerge at 2.5, 2.4 GA. As always, this would likely be an oversimplification. So there are multiple lines of evidence that support a limited exposure of continents in the Archean. This includes, for example, the oxygen isotope composition of seawater, the Archean sedimentary record, as well as numerical modeling. And there are some researchers that have suggested that Earth was more or less covered by a global ocean throughout more or less the entire Archean. But this is inconsistent with other evidence, including Archean siliciclastic sediments that derive from emerged continents, as well as the local occurrences of magmas that interacted with surface water, and also the local occurrence of subaerial lava flows. So it is unlikely that Earth looked like this here, like in the picture on the left-hand side throughout the entire Archean. And perhaps a more realistic model is that we had at least small microcontinents sticking out of the ocean. So maybe a little bit like this picture here on the right-hand side of the Whitsundays. Obviously, since we're talking about the Archean, minus the trees and definitely minus the boats, but you get the idea. And the reason I'm telling you all this is that I just showed you all these different geochemical proxies that indicate that the importance of subaerial continental crust and the weathering and erosion of the subaerial crust increased at the Archean Proterozoic boundary. But I don't think that it was a process like an on-off switch, where we went from more or less purely submerged continents to modern day level continental exposure. So perhaps instead of saying the emergence of continents, which to some people always seems to apply like an on-off switch mechanism, which is not what I'm suggesting, it is better to say that we had an increase in subaerial continental area at the Archean Proterozoic boundary. Coming back to this figure, if you remember the title of my talk, you know that I'm not only going to talk about continents, but also about atmospheric oxygen. Because temporally overlapping with these changes in the zircon and shale oxygen isotope records and the seawater strontium curve, Earth atmosphere, or the oxygen level in Earth atmosphere rose. And this oxygenation event in the Paleoproterozoic is termed the Great Oxygenation Event. Before the Great Oxygenation Event, we had no or only negligible amounts of oxygen in the atmosphere, and then oxygen levels rose. And this rise of oxygen is recorded by many different proxies, but perhaps most prominently in the multiple sulfur isotope record of sediments. And that's what's shown here at the top of the figure. And I'm going to talk about this in a little more detail later. So for now, I will just tell you that what you see here is that these large non-zero Kep delta 33S values disappear starting from the early Paleoproterozoic. And this disappearance of these non-zero values is linked to changes in atmospheric chemical reactions related to the rise of oxygen. So yeah, ultimately, this is the question that I would like to address in this talk. Is there a link? So did continental subaerial area increase in the early Paleoproterozoic, and was there a potential link with atmospheric oxygenation? So far, I focused on the geochemical record, but let's have a look at other evidence that is not purely geochemical to get a more integrated picture. It has been suggested that aeolian depositional systems become more widespread starting from 2.4, 2.45 GA. Now, there is one publication that suggests that there is an aeolian system much older than this at 3.2 GA in the Moody's group, and we heard Andy's talk about this a while ago, that perhaps the evidence for aeolian deposition in this case is not super robust, but regardless, it appears like around 2.45, 2.4 aeolian systems become more widespread. It has also been suggested that we had a significant increase in subaerial volcanism, and this is something that was suggested based on the large igneous province record. And Lee Kump and Mark Barley were the first one to propose this, as far as I know. So this paper here is a paper that rightfully is very heavily cited, and it's a great study. It is often cited to argue for the emergence of continents at 2.5 GA. And what I'd like to point out is that if you look into the supplementary material of this paper, you'll see that they made the assumption that all post-Archean continental large igneous provinces are subaerial, which is something that we actually don't know very well. So we know that in the Phanerozoic, most, if not all, continental large igneous provinces are subaerial. And we also know that in the Archean, there are quite a few continental large igneous provinces that erupted on submerged continents, but we don't actually know very well when this change occurred. So we looked into this in a little more detail. And the idea behind this study was to use the continental large igneous province record as a more direct record of subaerial exposure of continents as compared to geochemical proxies. So this figure here shows the frequency of continental large igneous provinces between 3.5 and 2 GA. And again, we focus specifically on continental large igneous provinces because they can tell us something about the exposure of continents, whereas oceanic large igneous provinces can't, or at least it's not as straightforward. So these are the criteria that we used to classify the eruptive environment, that is subaerial versus submarine. And this is predominantly focused on the extrusive parts of the large igneous province. If present, we can also use intercalated sediments to determine the eruptive environment. The only problem is that for a lot of Precambrian large igneous provinces, the only preserved remnants are actually intrusive rocks, like silts or dike swarms. So in those cases, it's a lot more challenging, if not impossible, to classify the eruptive environment. In some cases, we could still do it based on correlations with intracratonic sedimentary successions or other volcanic rocks if precise enough and robust age constraints were available. But yeah, it's a lot more challenging for intrusive rocks, obviously. So we managed to classify about a third of all of these events. And as you can see, at around 2.8, the first subaerial eruptions start to pop up. And those are in the Pilbara and in the Cupwall Craton. And then we have submarine volcanism again for a while. And then around 2.5, we have some more subaerial eruptions in Canada and the Hearn and in the Cola Karelia cratons. And then between 2.4 and 2.2, all classified continental large igneous provinces erupted subaerial and on many different cratons on a global scale. So if we consider only the classified events and then normalize those to 100, it's a little easier to see changes in proportion of subaerial to submarine volcanism. So that's what's shown here by the solid black line, that's our study. And then Camp and Barley study is the dashed line. And as you can see, they're actually quite similar. Not quite the same, but similar nonetheless. So we interpret these time intervals of increased subaerial lip volcanism to be indicative of high freeboard conditions, or in other words, time periods where we had large areas of continental crust exposed subaerially. And this actually agrees very well with the sedimentary record as well. So these gray boxes here at the top of the figure are low freeboard conditions and high freeboard conditions as inferred from the global Precambrian sedimentary record. And this is not something that I came up with. So using the sedimentary record is not always straightforward because it can be very challenging to get precise age constraints or age constraints in general. And I'm no expert in sedimentology anyway, but luckily others have looked into this before. So these are two papers by Erickson and others, and they suggest that there is a circa 2.4 basal unconformity that is pervasive on 6 different cratons, which they interpret as being related to a rapid sea level drop. And then furthermore, they suggest that the time interval from 2.4 to 2.2 GA was a time of globally high freeboard conditions, followed by a drowning event. So this all seems to agree really well with what we see in the large igneous province record. So coming back to this, I've now added our large igneous province study here, the gray boxes. And yeah, as you can see, many different lines of evidence support an increase in freeboard at around 2.4 GA. So this brings me to the second half of my talk. Is there a link between increased subaerial exposure of continents and atmospheric oxygenation? Part 2. So for this part, we had to collect a sample set that was as representative as possible of a global process, so a global sample set. And I didn't collect all of these samples myself, but I did get the chance to do quite a bit of field work during my PhD all around the world, which was pretty cool. I just wanted to show some photos. So we have Ghana here, then China, and then the States. And during these field sessions, we targeted sediment-derived granitoids, Archean to Proterozoic sediment-derived granitoids. They are strongly pyroluminous and contain pyroluminous indicator minerals such as primary muscovite and garnet, which is indicative of a sedimentary precursor. And the idea behind targeting sediment-derived granitoids was that these samples allow us to analyze multiple different isotopic proxies within the same samples, including proxies for atmospheric oxygen level and continental recycling, and then tie those to an age, the crystallization age of these samples. Specifically, we looked at sulfur and oxygen isotopes, so I don't have to go over this again. You already know that oxygen isotopes track supracrustal recycling and potentially also freeboard conditions. And sulfur isotopes, multiple sulfur isotopes especially, are an excellent tracer for atmospheric oxygen level. So I've already showed a very similar figure to you before. We have here the global sulfur isotope record of sedimentary sulfides and sulfates. This is expressed as Cap delta 33S. And this blue bar here marks the timing of the great oxygenation event. And as you can see, before the great oxygenation event, we get these large non-zero Cap delta 33S values, which indicates mass-independent fractionation of sulfur isotopes. And you can only generate these signatures in an anoxic atmosphere. After the great oxygenation event, we get Cap delta 33S values close to zero, which indicates mass-dependent fractionation in an anoxic atmosphere. And I'll just go straight to the results. These are delta 18O values as measured in garnet and zircon from these sediment-derived granitoids. There's also some literature data in there. And as you can see, perhaps unsurprisingly, we see this increase in average delta 18O like we see in the global zircon record, also in these samples very prominently. The blue bar again marks the timing of the great oxygenation event. So in comparison here, the shale record, again, we talked about this already at the beginning of the talk. There are quite a few more data points to the left of this figure, just outside the figure, to constrain the Archean shale oxygen isotope composition. So as you can see, this increase in delta 18O in our sediment-derived granitoids and the decrease in Cap delta 17O in these shales seems to be temporally linked. And again, this has been interpreted to be related to the onset of a modern hydrological cycle over large subaerial land masses. So we interpret this increase in delta 18O in sediment-derived granitoids to be related to the increase in delta 18O in sediments. And then when these sediments were recycled into the igneous rock record, we get these signatures. And sulfur. So before the great oxygenation event, the granitoids that had pyrites, these sulfides, they show non-zero Cap delta 33S values. And even though the magnitude of these signatures is relatively small, they're clearly outside the range of what can be achieved through mass-dependent fractionation, which means that these granitoids record the recycling of atmospheric sulfur into the igneous rock record, and they indicate an anoxic atmosphere. Whereas then, after the great oxygenation event, we get Cap delta 33S values close to zero. So to conclude, the increase in average delta 18O and the disappearance of the mass-independent fractionation signatures of sulfur in these sediment-derived granitoids seem to be coupled, which in turn supports a temporal link between the increase in freeboard and atmospheric oxygenation. And the question is there a causal link as well? So this will be my last slide. What could the causal link be? So it has been suggested that a decrease in volcanic degassing pressure associated with a shift towards more subaerial volcanism would lead to the emission of less reducing volcanic gases, therefore reducing the sinks for oxygen. Also, increase in subaerial weathering and erosion would also affect the nutrient cycle and would lead to an influx of nutrients from the continents, the emerged continents, into the oceans, especially phosphorus, which then could fuel oxygenic photosynthesis and therefore increase primary production. So that is it. And yeah, I thank you for your attention. And if you have any questions, then I'm happy to take them.